Okay, so hello everyone, welcome to EEEE lecture number 36 live, and today's date is 17/4/24. Let me put it to full screen mode. Okay, am I audible everyone? So, hello, y'all are there? Am I audible?
Yes, sir.
Oh, in between I was in between not there, right? Yeah, by mistake I pressed the aeroplane mode, so that's why. Anyways, we'll start now. So, we were discussing half wave rectifier, and we have completed its circuit diagram, the working, and input output waveform. Now we have to derive the expression for its average value of the output. So first of all, let's draw the output waveform, directly the output waveform. So if I want to draw the input also, we can draw that. So this is how my input waveform will look like, the secondary of the transformer. Okay, and my output waveform will be like this. Here it will be 0 because of the diode property. This is V out and this is Vm. 0, pi, 2 pi, 3 pi. How much is the period of this waveform? You don't know how to calculate average value? How much is the period of this waveform? Tell me. Is it pi or 2 pi?
2 pi.
Yes, because after 2 pi only it repeats itself. Your period is 2 pi. And your Vi is Vm sin omega t. So first derivation is finding the average value of output. That is, we have to find V out average, or it is also called as VDC. So let's start by finding the expression for V out average. So what is the definition of average value? You remember 1 by t, 1 by period divided multiplied by 0 to period into Vi of d omega t, right? I mean output. Sorry. Yes or no? So what is this period now? 0 to 2 pi. So from 0 to pi, you have Vi. Yes or no? D omega t. What about pi to 2 pi? It is 0. Agree? Come on, fast. Agree or no?
Yes.
Okay. So V out, please keep on writing. It will be 1 upon 2 pi, 0 to pi, Vm sin omega t d omega t. This is what we get. And here it is 0 d omega t. What is integration of uh, this will become Vm by 2 pi. What is integration of sine? Minus cos, right? Minus cos omega t, and omega t goes from 0 to pi. Okay, so V out average will be minus Vm by 2 pi. Let's take minus out. So it will be cos pi minus cos 0. What is cos pi? No, minus 1. Yeah. So here you will get minus 1 minus gets cancelled, and here you will get almost like Vm by 2 pi into 2, right? So how much is my V out average now? Come on. How much it is? Vm by pi, correct? Yes or no? And this is also called as DC, VDC. So how much is this DC voltage in terms of Vm? If I divide 1 by pi, how much is that? So VDC is around 0.318 times Vm, correct? Am I correct? Just check this number. So if I plot my output waveform, my average value of this waveform is how much? That is what it determines. So if this is AC signal, negative half it is 0. The average value of this waveform, the maximum is Vm. This is output. What is the average value of this? The average value of this is somewhere around here. Somewhere around here. VDC, which is Vm by pi. Okay. This is the DC component. And what is the AC component? Can you tell me in the waveform? This is AC. This is DC. V out DC, right? And this is around 31.8% of Vm. Agree? So Vm, let's say, is 10. So this will around VDC will be around 3.18 percentage value. Yeah, understood? So this output of half wave rectifier, when we call it a pulsating DC, we call the output of half wave rectifier as pulsating DC, means it contains AC plus DC. So here is my AC part and here is my DC part. Understood? Yes or no? You all are writing along with me, right?
Yes.
Okay. Now, I hope it is clear now. My output is pulsating DC. That means it contains a DC component in the form of average value and a AC component in the form of the peak value. And we don't want the AC component. We only want the DC component. Now, if I want to calculate output current average value, how will I do it? Do I need to derive again? No. It's also called as IDC. So, which is nothing but V out average divided by RL. That will be VDC divided by RL. And how much is VDC? We calculated just now, right? It's Vm by pi RL. Okay. And this Vm by RL, we call it Im. So therefore we can write I out average is equal to Im by pi. Okay. VDC is Vm by pi. I out average is Im by pi, where Im is Vm upon RL. Okay. So this is average output current, load current. I hope you have written it down. Completed?
Yes.
Yes, sir.
Okay. Because we have a lot of mathematics to go now. This is the first derivation. Average value of the output. Here it is. So average value of the output is 31.8% times the peak value, the maximum value. Here it is. Now, let's go to next part, B. You have to derive V out RMS. So RMS component कितना है? V out RMS. So RMS value of AC component of output. Alright, so we'll write V out. What was the formula? V out square RMS is 1 by T integral 0 to T V out square d omega t, I mean V out square of omega t d omega t. Okay, where period is 2 pi. Again here Vi is Vm sin omega t, and from 0 to 2 pi, 0 to pi only we have to consider, plus pi to 2 pi is 0, correct? So let's write V out square RMS is equal to 1 by 2 pi. Here it is 0 to 2 pi. Oh, I'll write it as pi only right now. Yes or no? 0 to pi. Why 0 to pi? Because pi to 2 pi is 0. See, from pi, this is, let's say, pi and 2 pi. From pi to 2 pi, the output is 0. That's why we are not considering in the integral. So 0 to pi. What is V out square? Actually, Vi. Okay, here it is. See, at the start we have written that V out is equal to, in the previous lecture we have written. See this, V out is equal to Vi, which is Vm sin omega t from 0 to pi, and from pi to 2 pi it's 0. Okay, so based on this, V out square will be Vm square sin square omega t d omega t. Now Vm square will take out what is sin square omega t written as? Anyone remembers what we did before? Vm square by 2 pi. What is sin square theta? Can we write it as 1 minus?
Minus cos 2 theta by 2.
Yes, 1 minus cos 2 theta by 2 d omega t. Okay, so we proceed forward now. V out square RMS is Vm square. This 2, this 2 as it is, let it be, divided by 2 pi. So first integral will be omega t, right? By 2 minus, what is integral of minus cos? I mean cos sine, na? So sine 2 omega t by 4, because coefficient of omega will come. Are you getting it? Omega t going from 0 to pi. Understood this? Yes or no? So V out square RMS is Vm square by 2 pi. Omega t is pi by 2 minus 0 minus sine 2 pi by 4 minus sine 0 by 4. Okay, what is sine 2 pi? This is 0, this is also 0. Okay, so what are we left out with? V out square RMS is Vm square upon 2 pi into pi by 2. Okay, this is Vm square by 4. So what is V out RMS? Vm by 2, correct? And that is exactly the formula. Okay, so please note it down. I hope you have completed up till here. What about I out RMS? It's Im by 2, where Im is Vm upon RL. Agree? Okay. When you completed this, please let me know. Have you completed this?
Yes.
Okay. The next derivation is of rectification efficiency. So write down the third one. or rectifier efficiency. How efficient is my rectifier converting AC to pulsating DC? So write down its definition first. It is the ratio of DC power at the output to the applied input AC power. Okay, so mathematically we can write percentage efficiency is given by PDC upon PAC into 100. This is the formula for rectification efficiency. Can I continue? So PDC will be given by IDC into VDC. Yes, or it can be written as V square by R. I mean VDC square R, and or it can be written as IDC square into RL. So V into I, V square by R, and I square R. Same thing, right? Yes or no? Then PAC, it will be V out RMS into I out RMS, or we can write VRMS. Sometimes we can drop this I out a term and we can write RMS VRMS, or it can be written as VRMS square by RL or IRMS square into RL. Are you getting it? Same formula, V into I, V square by R, and I or I square into R. Fine. Now we have to calculate PDC. So how much is PDC? Let us individually calculate. It's Let's use this formula, VDC square upon RL. How much is VDC? We have found out Vm by pi, right? Square divided by RL. So how much is this now? Vm square upon pi square RL. Let's call this equation number 1.1. Now next we calculate PAC. So PAC also we use the formula VRMS square divided by RL. And how much is VRMS? Vm by 2, the whole square divided by RL. That will be Vm square upon 4RL. Let's call this 1.2. And now what is the rectification efficiency given by? Therefore, the rectification efficiency is given by PDC upon PAC into 100. How much is PDC? Vm square upon pi square RL. And how much is PAC? Vm square upon 4 times RL. And this into 100. Something gets cancelled out? Yes or no? Vm square gets cancelled out, RL gets cancelled out. What do we get? Tell me, what do we get? 4 divided by pi square into 100. How much is it? Calculate this and let me know. How much is 400 upon pi square? Come on, tell me fast.
40.56.
So 40.56 is my efficiency of half wave rectifier. HWR, when I write, it's a half wave rectifier. So that's the efficiency of half wave rectifier, meaning out of 100% DC input power, only 40% is getting converted into pulsating DC. Rest is a waste of energy. So not a very good efficiency. Okay. So this is the way you can derive the efficiency of rectifier, of a half wave rectifier. The procedure will remain same for full wave, center tap and bridge rectifier. So don't you worry about that. Alright. Can we go to the next derivation? Ripple factor. Okay, let's start. This is number 4. Ripple factor termed as small r. Write down its definition. It is the ratio of RMS values of output AC component to the DC component of rectifier output. Okay, it is the ratio of RMS value of the output AC component to the DC component of rectifier output is the ripple factor. Okay, so we can define it as R is equal to IAC upon IDC, where IAC formula will be square root of I out square RMS minus IDC square. Therefore, if I divide by IDC, I'll get here I out square. I can write it as I RMS square divided by IDC square minus 1. So I've just divided by IDC. So when it goes inside, it becomes IDC square. I hope you are following. And this is nothing but R. So R is square root of IRMS square divided by the average value of the output. Okay, so this is the formula for the ripple factor. Please note it down. You don't have numerical for this, so you don't have to worry about solving this. Now, for a half wave rectifier, I am writing in short form. For a half wave rectifier with resistive load, what is IRMS? Im by 2, right? And what is IDC? Im by pi. So substitute these values over there, you will get R is equal to square root of Im square by 4 divided by Im square by pi square minus 1. So it's basically square root of pi square is inside the bracket, pi square by 4 minus 1. How much it is, calculate? How much is pi square by 4 minus 1, the whole root of? Anyone? Anyone with the answer?
1.21.
Yes. So ripple factor is 1.21 for half wave rectifier. Oh, 1.12 I've written. 1.21 for a half wave rectifier, meaning in terms of percentage, it's 121%, which is very, very bad. So we don't use half wave rectifier ever in any practical circuit. We either use full wave, center tap, or bridge rectifiers. Okay, so this completes the analysis for half wave rectifier. Only TUF is left, transformer utilization factor, that we will do it together for all three rectifier circuits. Okay, so now we can go ahead and start with the full wave bridge rectifier and do the similar analysis to it. Okay, so we have two options, whether I'll go through the entire writing work again or I'll show you the work. I mean how I did today. like I've derived everything right here, the circuit diagram, the waveforms, the cases, the case 1, case 2, then the input output waveforms. You want me to continue like this only in the same manner?
Yes, sir.
Okay, all right, we'll continue in the same manner. So first of all, have you completed all this? Are you ready for the next part, for a full wave center tap?
Yes, sir.
Okay, let's start now. So here only we'll continue. So write down the heading: full wave center tap rectifier with R load. Okay, whatever we may cover till 7:30, we will cover it, or else then left out part will cover on tomorrow's class. Okay, full wave center tap rectifier with resistive load. So first of all, let me start with the circuit diagram, the same sequence. Circuit diagram working, input output waveforms, and the analysis. So first is circuit diagram. So please draw the circuit diagram. Here we'll draw a little bigger. Um, okay, these are primary windings, and then I'll draw the secondary windings. These are secondary windings. Okay, this is my AC mains. Okay, I have to change the color over here. This is AC mains. AC main is single phase 230 volt, 50 hertz. This is center tap transformer. Center tap step down transformer. This one. Center tap step down transformer. I will tell you how does that work. You take the tapping from the center and that you connect it to the ground. Okay, there are two windings here. This is one, and this is the second one. This here you connect the resistor RL, and this is V out going to the ground. Okay, many people draw the circuit like this also. Let me show it to you so that you don't get confused. They draw resistor here also like this, because this is the same resistor going to the ground. So if I draw it like this, it doesn't it's not wrong. Okay, and they show the output over here. That will create unnecessary confusion. That's why I've taken it out. It one and the same thing. So this ground and this ground are one and the same thing. Okay, what I mean is this yellow color ground, this ground and this ground are common point. Are you following? Remember, a transformer has two jobs. One is to either step down or step up the input AC mains voltage. Second job is to isolate AC mains from the circuit. So remember, AC mains is how much? This has a separate ground. Iska separate ground hai. So transformer not only just steps up or steps down, it also electrically isolates AC mains from the remaining part of the circuit. So these are my two diodes, D1 and D2. Okay, here is the center tapping. This is the center tapping. Okay, so here we get a zero voltage. All right, Now what did I tell you? This transformer, center tap transformer converts what? Which voltage to which voltage? High AC voltage to low AC voltage. Yes or no? Now that low AC voltage gets splits up into two parts. Let's call this as, let me highlight this as point A, this as point B. Okay, and let me call this voltage as Vi by 2. So here, from here to here. So from here to here, positive negative. Huh? From here to here, positive negative will be again Vi by 2, but they will look differently. They will be out of phase. So here it will look like this, and here this Vi by 2 will look like this. Are you understanding? They are 180-degree out of phase with each other. Are you getting what I'm saying? This Vi by 2 is like this Vi by 2 is like this, and together they represent Vi. So this total is Vi. I'm not drawing it. So for example, we have 12, 0, 12 in our lab, the center tap transformer. So this is at point A 12, 0 here, and at point B also 12. Here it is. Okay. So that means Vi by 2 is the secondary voltage of the transformer. That is 12 volt. Example. Okay, that's why we write 12 volt, 0, 12 volt. Are you following what I'm saying? But what is Vi called as? Vi is the secondary voltage of transformer. Abhi, what do you mean by center tapping is, let's say these windings, number of windings are 100. So let's say these windings are 20. So at 10th winding you center tap it. I mean you center tap at 10th winding. So 10 windings are for above, 10 windings are for below. So at the above we have Vi plus 2, and below you have minus Vi plus 2, that is 180-degree out of phase. Are you getting it what I'm saying? Yes. So whenever we have, let's say, phi dash phi, it means this is Vi by 2 dash Vi by 2. So total voltage Vi will be 10 volt. Are you understanding? So this gets split, the 10 volt gets split into 505. Here we have total 24, but that gets split into 12 to 0, 0 to 12. So that is overall 24. Did you get it what I'm saying? So Vi by 2 is 12, so Vi will be 24. Your Vi by 2 is 5, so Vi will be 10. Understood this? Yes or no? Tell me. Because this is the tricky part. Understood about the center tapping? Why it is called as a center tapping? Because at the right at the center, at the 10th winding, there is a tapping and that is going to the ground. So we have equal tappings at the there are two secondaries. One is positive Vi by 2 and one is negative minus Vi by 2. Did you understand this much? Hello? Yes, no, tell me.
Yes.
Little bit you have understood, or should I explain again?
Explain again.
Okay. I'll just explain the transformer part. So let's say if I have, this is my transformer. Okay. This is primary winding. Remember, this is primary winding. Then I have this iron core. This is my AC mains. Okay. 230 volt RMS, 50 hertz. Then at the secondary tapping, we have less number of turns, right? Okay. So here we have point A. Let's call this at point right at the center of this tapping. We keep it to ground. Okay, and this is point B. This is point O. Okay. So total voltage over here, let's say it's supposed to do by 10 is to 1. So this voltage should be around, let's say this is 240 volt instead of 230. Alright. So with the ratio 10 is to 1, primary winding and secondary winding ratio 10 is to 1, 240 gets converted into 24 volt. This much you agree? So between A and B you have 24 volt. Yes or no? Hello? So between 0 and A you have Vi by 2. So between 0 and A you plot the waveform like this, SA. But this is 12 volt. Okay. Now between 0 and B there is another Vi by 2. So this is total Vi. Okay. It gets split into two parts, Vi by 2 and Vi by 2. Okay. So between 0 to B the waveform is same amplitude but it starts with out of phase. Here it is like this. So this height is also 12 volt. Now did you get it? Yes or no?
Uh, huh.
Now this voltage at point A, if you measure the voltage it will read 12 volt. At 0 if you measure the voltage it will read 0 volt. And at B if you measure the voltage it will read again 12. Okay. So at A and B if you plot A and B you'll get the waveform like this. It will be A minus B, so both the waveforms will get subtracted and you will get total value of peak will be 24. Understood this? So this gets splitted into this part OA and OB. This is 24 and this is your VI. This is your VI which gets splitted into 12, 0, 12. Okay. So from 12 to 0 it's a positive, from 0 to 12 is negative. And here Vi, this is Vi. Vi is your secondary voltage of transformer. Okay, so this is the best I can do. I hope you have understood this. What is the center tapping? Okay, followed this? Understood, yes or no?
Yes.
Huh. Okay, so now come back to the diagram. Now we have to, this circuit diagram you have to draw. So this is your circuit diagram for full wave center tap rectifier with resistive load. Now we'll explain the working in two cases. So can we start now? In the positive half cycle and in the negative half cycle, okay? Can I? Okay,
Yes.
let's start. Case number one. During positive half cycle. During positive half cycle of input or VI, sorry. During positive half cycle of VI or we can write input, no problem. This is input only. This is the output of the secondary transformer. It's fine. Secondary to the positive half cycle of the input, what happens? So I have to redraw the circuit one more time. Let me do that quickly. So we have these two diodes. I have to draw a slightly, okay, here we have a center tapping. Here we have two diodes. Okay, here we have AC mains. Okay, this is positive half cycle means this is plus, this is minus. This A, this B. This is plus, this is minus. Okay, this is ground. So tell me which diode is on, which diode is off. And let me complete the circuit. This is RL and this is V out. So tell me which,
A is on.
sorry?
A
No, diode number you tell me.
D1.
Sorry?
D1.
Yeah. So during positive half cycle of the input, my diode D1 is forward bias. Hence it is on, correct? What about diode D2? We are receiving negative voltage over here. So will it turn on? No. So diode D2 is reverse bias. It is off. So diode D2 is off. So whenever diode D1 is on, it is replaced with a short circuit. Yes or no? So here it is my short circuit like this. And whenever diode D2 is off, it is replaced with a open circuit like this. Understood now? Yes or no?
Yes.
Yeah, and of course this is Vi by 2, this is minus Vi by 2. You remember that. Okay. So will the current flow in the output, and which direction the current will flow? Can you tell me the current will flow? Yes, it will flow via A, diode D1, resistor R, RL, output means, and then again back to O and back to A. Okay, so your I out will flow. This is I out direction down. I out will flow from A to diode D1, R, and then 0, here it is, and back to ground. Terminal 0 and back to ground. Okay, so the current will flow in the circuit and back to A basically. Okay, O to A. Next. Alright, so what will be my output now? Tell me. Output will be how much? This much, na? What is available over here? What is available over there? Vi by 2. Are you understanding? This much output will be available here. So this will be Vi by 2. Understood? Yes or no? And output I out will be V out upon RL. So please note it down. So we are into positive half cycle like this. We are over here. And this is Vi, which gets split up into two parts, Vi by 2 and your Vi by 2. Okay? Can I move ahead now?
Yes.
Okay, case number 2. During negative half cycle of input. Okay, so what happens? Let me draw this. This is AC mains. Okay, these are the center tapping. These are my two diodes connected to the load RL, resistive load RL, and here is my output. These 2 points, ground points, are one and the same. Now tell me which of the two diodes are on. So let me show you the polarity. Negative half cycle matlab this is negative, this is positive. So this point A with respect to B is negative. Tell me which is on,
B.
which is off. Yes. So during negative half cycle of the input, D2 is forward bias, hence it is on. What about D1? Reverse bias,
Negative.
hence it is off. Okay, so it is replaced with a, here it replaced with a short circuit and here is replaced with a open circuit, correct? So how will the current flow from B, D to RL, ground, O to A? Yes or no? So how will the current flow? Let me mark over here like this. Again in the same direction, it's going down. So I out flows from B D2 RL ground O back to B. Okay, this is how the current will flow. Yes or no? The current will complete its part like this. So I out flows. Do you agree? Yes, no, what? Hello.
Yes.
Alright, very good. So now, so both the half cycles, the output is flowing, output you are getting. So what is the output here now? Tell me. So output here is minus plus minus Vi by 2. So still it is positive Vi by 2. Okay. Why positive Vi by 2? Because input itself is reversed. So here that will be positive Vi by 2.
नेगेटिव होगा.
No, why negative? Tell me why negative? Because input itself is negative, right now. In negative half cycle की बात हो रही है ना, input itself is negative. So कोई भी negative voltage it will look like positive only ना. See, we are in a negative half cycle na.
Yes.
So that will read proper only. This will be plus Vi by 2, not minus. See this sign, polarity देखो, plus minus. This is also plus minus. So ये positive होगा. Okay. So both the cases output is Vi, it is follows the input Vi by 2, Vi by 2. So if I plot the waveforms, rough waveforms for the input signal, if this is my input signal, let's say it's Vm and minus Vm, I am plotting output. So the output signal will look like this. For the positive cycle, it will follow the input D1 is on. For a negative cycle, it will follow the input. Yeah, you are right. This will be, I think, negative. Yeah, correct. You are correct. This will be negative. No, it will be. I mean, you if you want to write it intellectually, yeah, it will be positive. But if you go into negative half cycle, it will be reverse of the this thing. It will be positive only. Yeah, it will be positive. But for negative half cycle, it is positive. So it's going up above. That's what we have to justify. And for the next cycle also, it will continue. D1 is on. So in the positive half cycle, D1 is on. In all the negative half cycles, D2 is on. Understood this waveform? This is called as full wave rectified output. Agree? Yes or no?
Yes.
Okay. Now let's plot the input output waveforms and complete the analysis. So before going there, let's clarify one thing. Let me connect my writing pad again. हाँ. V out is equal to Vi by 2 if we write, let's consider this as Vm sin omega t. Okay? If this is pi, 2 pi, 3 pi, repetitive. So from 0 to omega t, this is omega t. 0 to pi, it is Vm sin omega t. And again, from pi to 2 pi, again it is Vm sin omega t. So all the period it is Vm sin omega t. So this is very important in solving the analysis. Vi by 2 we consider Vm only. Vm sin omega t, Vm sin omega t. So there is no confusion at all. Okay. Vi is the secondary voltage. Vi by 2 is the two secondary voltages at the tapping. Now can we draw the input output waveforms now quickly? Shall we? So let's start.
सर एक सेकंड ग्राफ.
Graph will draw it again. This will draw it again.
ओके.
Okay. So let's properly draw the input output waveform. So write down input output waveforms with respect to time for full wave center tap rectifier. So let's first draw input secondary voltage. This is omega t. Let me start with color blue. Let's call this as, that's it, this as Vi by 2, right? And this is Vm and this is minus Vm, correct? This is pi, this is 2 pi, this is 3 pi. So how will be the output waveform looking like? This is output waveform. How will it look? It will follow the input, it will follow the input, it will follow the input. Here into positive half cycle only. So your D1 is on, D2 is on, D1 is on. So this is output. Okay. Now if I want to plot current waveforms, how will I do it? I out मुझे plot करना है. So will it be the nature will be same? बताइए. Will the nature be same? Yes. Why not? Only the magnitude will be different. So nature might be, the height will be different because this is V out by RL, which is Im. It is nothing but Im. Okay. Understood this? Now,
सर जो आपने रेड से बनाया है उसका भी हाइट छोटा होगा ना, हाफ होगा.
no. Why?
जो V/2 है ना.
No, 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 no. You're not understanding. See, Vi might be 20. Okay. Vi by 2 might be 10. Correct? तो हम लोग इसका ये प्लॉट कर रहे हैं, ये रहने दो, नॉट दिस.
जो
यू आर
ऊपर
प्लॉटिंग
नीचे
दिस.
दोनों 10 वोल्ट्स है ऐसे.
हाँ, 10 0 10 है ये. सो वन साइकिल में 10 आ रहा है, दूसरे साइकिल में भी 10 आ रहा है. सो इट्स 10 0 10. डोंट वरी, इट्स अ साइनसॉइडल सिग्नल ओनली ना. Okay, so do not worry, it's Vm only. So if this is my, I'm treating this as my input. So output will follow the input, na? In the positive and negative half cycle, output will follow the input. Or maybe I should write one lines over here, few lines here, that your output V out follows input, which is Vi by 2. Okay. अच्छा, यहाँ पे बताओ, यहाँ पे मेरा VD1 कितना होगा वोल्टेज? Voltage across the diode. Anyone else? Can you tell me? Only one
V
person. No, no. Let's say Vi by 2 is Vm. Let's consider Vm only. So कितना होगा बताओ? ये पॉजिटिव ईडर होता है, नेगेटिव ईडर होता है. सो VD1 कितना होगा? अरे शॉर्ट सर्किट है ना. VD1 विल बी,
VI.
अरे VD1 इज जीरो ना, शॉर्ट सर्किट है.
हाँ.
What about VD2? Here it is plus, here it is negative. So ये प्लस है, ये माइनस है, तो it will be, what will come? This is minus here, this is plus here. So it will be minus Vi by 2, which is minus Vm. Correct?
हाँ.
हाँ. This is during the positive half cycle. On negative half cycle, में what happens? Again, I should write there. Output follows the input. Follows the negative of, I mean, output follows the negative of input, right? In a negative half cycle. Okay, now tell me what is VD1 over here? Plus minus VD2 will be 0, right? What about VD1 plus minus? So this is plus, yeah, this is minus, this is minus, this is plus. So minus Vi by 2, which is minus Vm again. Understanding? This is during negative half cycle. Now if I plot this VD1 and VD2 separately, let's say, so students, if I plot this VD1 and VD2, what I should get, tell me, how will I plot it? This is VD1, sorry, this is VD2, VD1. How will the waveform look like?
half wave rectifier.
Nahi, no. Half wave, but it will going negative. See, it's the peak inverse voltage. It can handle negative voltages, right? So, for positive half cycle, VD1 is 0. For negative half cycle, VD1 is minus Vm, correct? So, the waveform will look like this. See this. ऐसे दिखाई देगा, देखो. This, correct? This is VD1. And this value will be minus Vm. Is this visible to you, this color? No?
Yes.
Okay. And what about VD2? VD2 is negative minus Vm in the positive half cycle and 0 in the negative half cycle. So here it is negative and here it is 0. Oh, sorry. Here it is negative. So this is minus Vm. So this is VD1, this is VD2. So what is the PIV rating for diode 1 and diode 2 over here? It is minus Vm only. Meaning the diode should withstand a voltage of minus Vm across it without getting damaged. So this is the PIV rating of diode D1 and D2 for a positive half cycle. Understood this? Yes or no?
Huh.
Now,
So diode is negative voltage, but the rectifier are positive exercise.
VD1 and VD2 just have drawn it for your more information for your negative voltage. But the output voltage across, see, diode voltage and output voltage is different, hai na? Output voltage is over here, diode voltage is over here. I mean to say, how do you select a diode which will not break down? So we have to consider this VD1, VD2 waveforms also. But in the exam, if you draw Vi by input, output and I out, that is sufficient. So ये waveform को देख के, what do you think? What is my V out average? Positive ना?
Hmm.
What about I out average?
Positive.
Yeah, and that is what we want. Positive DC component. So these are my input and output waveform with respect to time. So now we have a few things left. You want me to cover tomorrow or you want me to cover today? Because it will take around 20
Tomorrow.
minutes more. So we have derivation for expression for rectification efficiency, ripple factor, and V out average, V out RMS for center tap. I mean full wave center tap transformer. So this will can we continue tomorrow in a tomorrow's class? It's almost 1 hour now.
Yes.
Hello everyone.
Yes, sir.
Okay, yeah, because we should also have a limited capacity to take in. So we'll end here, and next time, that is tomorrow, we'll cover the expressions of V out average, V out RMS, rectification efficiency, R for full wave center tap rectifier. Okay, so this will cover next lecture. Alright, so that's it for today. We've completed 36 lectures today. Next we'll cover this in 37 lecture, that is tomorrow's lecture.